Okay, so Aurélie has been navigating for more than 10 years in computational sciences applied to engineering, medicine, education, economy, finance, or journalism. After 9 years in the US in organizations such as MIT or Bloomberg, Aurélie lives and works today between USA and France, where she leads in Silico Veritas, a development agency in computer modeling and analytics. Aurélie is a senior advisor at the Boston Consulting Group and Altermine, mentor of the Frontier Development Lab at NASA, teaches algorithm in graduate schools, mostly at MIT, conducts her research on algorithms, and writes for Le Point, Europe 1, and Elle International on sciences and technology. Aurélie is also an external collaborator for the Ministry of National Education of France. And last but not least, she recently published a bestseller entitled De l'autre côté de la machine, in which she talks about algorithmic bias in AI. So she's also a media star. Aurélie, we are delighted to welcome you at this seminar. Thank you for coming, and the floor is yours.
Thank you, Gerard. So I decided to give this title to my presentation. Oops. Okay. Mathematics is everything from research lab to a newsroom. So actually, Pascal Massard asked me to present my vision on mathematics and why mathematics are key in every single domain, disciplines, and in our life on a daily basis. And so I thought that I could take my own experience and what I've been doing, what I still do today, what I've done, using mathematics in a broad range of disciplines. So I'm going to start with this quote that I love from my friend Emmanuel Schanzer, who is a computer scientist and founder of Bootstrap World. Some people might know it in the United States. So he said to me, every single kid is a data scientist. And I love that quote because it actually refers to the fact that when you're a kid, you tend to use numbers very easily. You tend to compare sizes, length, time duration, such as I'm going to run twice faster than you, and I'm going to eat 3 times more pasta than you, etc., etc. And in fact, it's years after that we tend to dislike sometimes mathematics, which is bad because mathematics are everything. So today, what I'm going to do and what I'm going to try to do is to explain what we can do with mathematics, and hopefully to keep saying this quote, every single kid is a data scientist, and hopefully say every adult is a data scientist. So first, I'm going to talk about some work that I've done. So everything that I'm showing here, it's part of the work I've done, the thing that I'm still doing at the end of the presentation, and it's in different areas to show the broad range of application of computer modeling. So first, it's the mechanics of synthetic soft matters. So here I'm going to talk about rubber. So this is the work I've done during my PhD, where I had to understand at the nanoscopic scale, understand the morphology of the carbon black fillers, carbon black particles inside the elastomer matrix at the nanoscopic scale, obviously, and try to actually model that morphology, then using computational mechanics to actually derive the local behavior to the macroscopic elastic behavior, to make the relation between what we see at the small scale in terms of morphology and elasticity, and what we experience at the macroscopic scale, still in terms of elasticity or the texture of the rubber. So this is what actually I've done. And to do so, what we've done is that we've used a domain which is mathematical morphology. So it's using the set theory to describe the different sets that combined all together can actually create a specific shape. So in that case, for the carbon black fillers, what we had to do is to combine at least three different kind of model to describe. So it was, just for you to know, 2 Boolean models and 1 hardcore model. And so those models were combined by using statistics, and measure theory to actually describe eventually the morphology of those grapes, those clusters of carbon black fillers within the elastomeric matrix, and then deriving those local properties, including morphology and elasticity, to actually obtain what we call the apparent and the effective elasticity of the material. So this is an example. It's an example in engineering, for synthetic soft materials, where we actually use mathematics for two things. the first thing is to actually to describe the morphology, the geometry, also over time of this material at the nanoscopic scale, which is the carbon black fillers, and then to derive, you know, to the macroscopic material behavior, you know, of this given composite. So this is an example. And by doing that, we were actually capable of capturing some phenomenon that was supposed by physicists and people in mechanics, but that was not really demonstrated using experiments. So we could see it inside the simulation at the nanoscopic scale. And so it was a big deal because we were also capable of linking the two scale, the macroscopic scale and the nanoscopic scale. So this is an example. Then if we move, we still stay in the soft material, but this time is in the human soft materials. So I have many examples, but I'm going to give you only 2 examples. So here it's a work I've done at University of so Penn State, the Penn State University. And also, I kept working on that when I was at MIT. So it's a work here on cardiac tissue engineering. So let me explain you. So what you see here is a heart, you know. And so after a heart attack, during a heart attack, what's happening is that some cells in the muscle here, what we call the myocardial tissue, are actually dying. I'm not gonna go into details, but just for you to remember that those cells are dying, and there are other cells that are creating collagen, which are the cardiofibroblasts that are creating more and more collagen. And so the tissue locally becomes stiffer. We talk about scar tissue. And we eventually talk about a heart that is tired. So it has some difficulties to pump normally. So some doctors are actually working intensively in trying to fix that in many ways. And one of the ways actually cardiac tissue engineering, the idea is to develop a cardiac tissue, a myocardial tissue, exactly, the muscle part, in vitro, in a lab, to replace the tissue that has been scarred due to the heart attack. So to do so, some medical doctors worked on this kind of materials here. So it's a material, we call it a scaffold. So it's a cordion-like scaffold in which in the pores, they actually put the cell, the cardiomyocytes, and they actually stretch the material and provide like electricity over time to actually mimic what's happening in the heart while living, you know. And then eventually they can recreate in vitro the tissue that is naturally in the heart. The issue that they had when they published this paper in Nature Materials is that for 2 things. First of all, the tissue they were obtaining in vitro in the lab was too stiff. The other was there were too many cells dying while regenerating this tissue in vitro. So we actually use, using analogy with the Campbell-Black fillers, it's actually a professor who hired me to use that model, to adapt that model, and to make it possible, you know, to use this kind of homogenization computational model to derive the macroscopic behavior of the final tissue after regeneration, and also to understand, you know, the mechanics between the cells, the collagen. So the collagen, you see an example, the collagen, there are a bunch of fibers like that, and the cells, the collagen, the cardiomyocyte, the collagen, and the scaffold, the pores of the scaffold in which the tissue is growing over time. And to do so, we use mathematical morphology, and I also use obviously some homogenization model, and those equations are very classical, you know, in homogenization. What is more interesting is actually this equation where we look at the strain amplification locally and globally. And thanks to those strain amplifications, we actually understood why some cells were dying at specific location within the pores and over time at specific time. And it was obviously due to the amplification. So in other words, due to the morphology of the tissue, of the pores, the way it was stretched over time, etc., the cells were actually seeing different type of stretching. And we know that you cannot stretch as much as you want, you know, a cell, because eventually the cell is dying. So this kind of thing. So we actually were capable of modifying the scaffold in which the tissue was growing over time, and to improve eventually the quality and to reduce the stiffness of the tissue eventually created. So this is another example where we use mathematics to model explicitly the morphology and the mechanical behavior of the cells, of the collagen, of also the material comprising the scaffold. And also we use mathematics and computer modeling and algorithm to derive those properties and from the local behavior of the cells, and their interaction with the collagen, we were capable of deriving those macroscopic properties to get the macroscopic elastic behavior of the heart regenerated in vitro to actually manage better this stiffness, and to reduce the stiffness by controlling locally how the tissue was growing. And we actually applied this method to another example in the heart, which is the heart valve tissue engineering. So the heart valves, for you to know, there are two valves, one here, that are opening, closing for the flow, the blood flow. And some kids are born with an issue with those valves. The synchronously is not good, etc., etc. So we have to replace those. And the heart valve tissue engineering is very promising because we use the kids' own cells to grow a heart valve in vitro, and then to replace the valve that is damaged, in the heart. So we had amazing results showing that how we can control the macroscopic behavior of the tissue regenerated using controlling what's happening locally, understanding what's happened locally between the cells, the collagen, and the scaffold. Another example is not on the heart, but on the brain, the traumatic brain injury. So here was an amazing study that we conducted with the team of Professor Raoul Radowitzki and John Janopoulos at MIT. So in this work, I had actually to model different things. To model, obviously, the brain in terms of morphology, but also plasticity, elasticity for small and large strain. And the goal here was to actually do something we cannot do in the real world, which is to apply a shock wave on the head of a human and see how the wave is propagating within the brain to better understand the mild traumatic brain injury. So we worked on the mild traumatic brain injury just because when you have a mild brain traumatic injury, you get the symptoms sometime 2-3 months after having it. So there is a delay, and this delay is very key here, because if we know in advance the risk of a human to experience this traumatic brain injury, we can actually assess it quickly and do a diagnostic as early as possible to treat the patient. And this is what actually we did here, because we developed a scaling law and an equation that was, so it's here, knowing the incident pressure, so the pressure that is prescribed on the head, and obviously there are other equations with the angle and everything, and knowing here it's a scale factor, what we call the scale factor. So it's actually a number, an indicator of the morphology of the brain, the skull, and the flesh, around the brain, depending on the species. So obviously it's different if you compare a human, a rat, or a pig. So, and we actually were capable, knowing the incident pressure and this parameter, to calculate the intracranial pressure. So in other words, we were capable of calculating the peak of this intracranial pressure. Hence, we know whether there is a traumatic mild brain injury and where it is in the brain. And by knowing where it is, it's very important, because you can relate that to the symptoms that you see in different kind of patients, depending on, which type of shock they experience on the head. So here is another example of how you can use math and computer simulations to actually first describe the morphology, and obviously there are other things that we've done to actually average, the morphology of the human head, for instance, looking at different ethnicities, gender, age, etc., etc. And here it's a good example on how you can use math and computer simulation to first describe this morphology, and then describe locally, the mechanical behavior of those materials, soft materials, and then to derive those macroscopically and to do the relationship. So this time it's the inverse relationship, because we actually, from the macroscopic shock, stress, force, we actually go into the small scales to get the local intracranial pressure. So then we move to a very different example, which is what I call, and sorry for the typo, it's the mechanics of stock market and economy news. So something very different. But here I want to show people how, when you have been trained on mathematics, computer simulation, AI, it can be machine learning or mathematical modeling, you can actually transfer this knowledge to other kind of application. And this is what I've done. So this is some of the work I've done at Bloomberg. So obviously here I cannot show equations, I cannot show anything because we haven't published anything, obviously, but I can show you the application. So when you work in finance, I mean, not in every single discipline, obviously, but most of the time you actually need to follow, if you work on the stock market, for instance, you need to follow the market, you need to follow the time series of different stock options and how it behaves, and try to find how it would behave, how it will behave in the near future. To do so, at Bloomberg, we use this function. So some people who are using, have been using Bloomberg knows that. It's what we call ANR. So it's a analyst recommendation function. So what do we do here? Well, it's a function that the finance players, actors are watching on a daily basis, where they actually can track the evolution of the stock option over time for a given stock option. And here what we do, the work I've done here, is that what we want to do here is to actually develop a model, so an AI model that can actually capture the best financial analysts. So let me explain. So here is an example. You have a list of analysts here. The finance analysts are the people who are analyzing the market and are providing the actors with some predictions, some how they see the market changing over time in the near, mid, and long-term future. So here's a list of analysts for a given stock. They actually give their recommendation, whether you should hold, you should buy, you should sell, etc., etc. And sometimes they give obviously a number. And so what we do at Bloomberg, we actually try to detect literally who are the good analysts and not as good for a given stock. So obviously you can see that some analysts are good for some markets such as energetic, for instance, and not as good for others. So it's interesting. So you need to develop models to capture those differences, to capture the performance of those analysts, and to create what we call a consensus, meaning that we can create a consensus of 20, 10, 5 analysts, but you have to build this consensus. So in other words, you have to pick the right analyst to belong to this consensus. So this is a model that, using what we see today for those analysts, we analyze the past. So how those analysts perform in the past for a given stock and different markets. And we can actually give a good consensus and a good average over the recommendation of those analysts belonging to the consensus. So it's a big deal, obviously, in the finance industry. Another example that I love, and I think it was the most exciting project I had, that was on the news. So here, and you might know Bloomberg for this, I think most of you. Bloomberg is a news media. So in other words, they actually provide the actors with news on economy, stock market, industry, etc., etc. And so those articles are actually written either there are articles from other media, like New York Times, for instance, but there are also articles written by the the journalists in economy from Bloomberg. And there are also a few articles that are generated automatically. So they are automated news. So here you have a list of news, and you click on them and you can see the entire news. And believe me or not, there are news that are created automatically. And I was working on that. So let me explain. I'm not replacing journalists. Don't get me wrong. So the idea is the following. We create model to actually, AI model to actually track the stock evolution, for instance, stock market evolution. And we try, based on the past, what's happened before. We try to capture the weak signals. We try to capture all those signals, that the key insights, that tells us something's going to happen. And we can also detect which things could happen. The thing here is, obviously, we don't do any prediction. It's not our work. Our work is really to capture the weak signals. Based on that, then we actually generate a very short news, like one title, 2 lines, saying, hey, this thing happened. For instance, let's look something very simple for Apple. The stock of Apple increased by 30% in the past 2 2 hours. The last time it's happened was, I don't know, 5 years ago, and this is what happened. And we try to do some correlation. And the thing is, by providing this automated news, and by the way, it's written automated news, so people know it's automated news. The journalist it's an alert to the journalist. So the journalists have then 10, 20 more minutes to write an article about this thing, because he and she's capable of writing about that. I am not capable, and my models are not capable. And then by doing that, we can actually capture the attention of the reader, and we increase the ratio of readings, of the article written by the journalist, because you capture the attention of the reader, so the reader then wants to know more about the factual news generated automatically. So here's an example. So those 2 examples of the consensus by measuring the performance of analysts, and here this is an example of capturing weak signals in time series to actually creating some alerts, to the readers and the journalists, are 2 examples where, in that case, mathematics and computer simulations are applied to a very different area, which is the finance and the news. But it's still very, very relevant here, because we need, when you analyze a time series, when you develop a predictive model, when you develop a model to analyze time series, in fact, you actually use pretty much the same mathematics. What you have to do is to work closely with the people who knows the discipline, the application. So here it was mostly, I worked with people who knew about finance and people who knew about economy. So that was a big learning curve, as you can imagine. So I'm going to finish with one thing that I'm working on. So we haven't published anything yet. It's DPIX. So with my business partner from Tel Aviv in Israel, so Dr. Philippe Benilouche, Dr. Grigory Ramsineou, and Annette Massé, we actually developed a toolkit, an AI toolkit, a model, an algorithm to literally predict the risk of a woman to develop a breast tumor in the next few years, from 1 to 5 years from now. And this technology is very key, because it's also an important day, because yesterday was the International Women's Rights Day. So we're very proud of this technology, and hopefully we're going to launch very soon the company. We're doing that now, and as well as publishing in a year from now the algorithm that we developed to capture and to anticipate the breast tumor development in the next few years for a woman. And finally, I want to finish with that quote from Bill Diamond, that you might know is the president and CEO of the SETI Institute and the NASA. He told me, and I love that, teaching space in elementary schools is the best way to teach all kids about science, because it is a unique application in which all science disciplines are involved. Well, I wish we could say, and we should say, that teaching math in elementary schools is the best way to teach all kids about science, because it's a unique application in which all science disciplines are involved. And I would say that it's a unique discipline in which that is involved in every single science, and that's why math should be more supported, in school, and we should be to be taught using games or anything to develop this attraction to that science. So I hope I convince you that mathematics are everything, everywhere. And I give my own example from this research lab to a newsroom, finishing with what I'm doing now in a research project that we started a year ago on breast cancer prediction. Thank you.
Thank you very much, Aurélie. So there are many questions in the chat, and some of them are technical and some of them are more
Sure.
on your so maybe a question: how do you define the best analysts? And your definition should depend on the magnitude of the forecast errors. What do you think of that?
So it's interesting. So there are many ways of doing that. First of all, we don't build one single consensus. In other words, we are building different kind of consensus because we want the people, the actors, to pick the consensus they want based on their own beliefs, and their own experience. So there are different ways. Obviously, I cannot go into details on that part because it was at Bloomberg. It's part of the company. But most of it, just for you to know, we were looking at the performance of every single analyst in the past for each given stock and each given industry. The industry is very much important because there are analysts who are amazingly good in some industries such as retail, luxury, energetic, etc., and we're not as good in others because analysts, their job is to find information to better capture the next move. So we were looking literally at their performance in terms of their past recommendation. That's it. We're not looking at how they were looking for how they research or anything. Obviously not, because we couldn't get this information. We're literally looking at the performance locally meaning for a given stock and a given industry, and globally as well. So it was like a balance between the global performance and the more detailed performance of the analyst.
Okay, thank you, Aurélie. Maybe a more personal question. What motivated you to move to the US after your PhD? And do you think you would have been able to carry out such research in France?
Well, it's interesting. I actually I moved to the US in 2009 because I had first experience at the University of CU Boulder. I was actually doing my first model in MATLAB. So it was a bit like a long time ago in MATLAB on the diffusion of chloride ions within concrete. So I really loved America. So I really wanted to go back there to do a one-year postdoc. And actually, well, I'm still there. So it's been 12 years. So it's a long time. I went there because I really wanted to discover new ways of working, and also so it was very to be curious, and then. The question is whether I could have done that in France. It's difficult because the only research I conducted in France was during my PhD, so I didn't see all the aspects of the research in France. What I can say is that when I moved to the US in 2009, it was not the best time to move. I mean, it was a good time to move because that way then you're there when you want to ask for a green card and everything, and you don't ask for a visa. But it was a tough time because it was a crisis. So a crisis for research as well. So there was not as many funds as we think, at that time. So it was hard to get fundings. But obviously the number are very different. You get much more money for a research project, but also you give more money to the university. On average 50% of your funds. So it's very different. The only thing that I can compare is really the people I worked with, because the people who hired me first were medical doctors and doctors of science. Next, my second employer at MIT was a computational scientist, but the first one was a medical doctor. And I was actually surprised that a medical doctor in 2009 decided to hire me. And things have changed, in France, but I don't think in 2009 a medical doctor would have hired me. Yeah, maybe not. Yeah.
And maybe a last question from myself. As you know, we are missing of women in math, in AI, and in machine learning. And my question is, which advice would you give to a young girl who is hesitating to start studying mathematics?
Well, I would show them this presentation to show them that they can do anything with math, anything. It's crazy. And I would tell them that it's doing mathematics, it's intellectually stimulating because you learn every day, literally. It's also, so it's very intellectually stimulating. It's also, you have the power. I always told the girls, I say you have the power to change the world because you model things, you understand things, you build models to understand mechanism, to predict, to simulate reality. So it's really, you have the power to change the world. And yes, and I tell them that because it's very, very much important. And I tell them that they can work in any field, in finance, in education, in engineering, sociology, anything. Like it's key. So they understand why they're doing it.
Aurélie, thank you very much. Merci beaucoup. And
Merci.
We are going to switch to the next speaker. Thank you very much, Aurélie.